Welcome to a Rice University digital media production. For more information about us, please visit our website at www.rice.edu.
All right, I think we'll begin. People are still coming in after class, but I'd like to welcome you all to the spring semester continuation of our Scientia lecture series on networks. My name is Susan McIntosh, and I'm the director of Scientia. Thus far this year, our speakers have outlined how network concepts provide real-world insights into how transmission systems operate. Examples have included the transmission of H1N1 flu virus, knowledge, and power. Today, the focus will shift to network robustness and resilience in the face of error and failure. An important insight that has emerged from the study of scale-free networks, those are networks which have a small number of nodes with a very large number of connections, and vice versa, is an understanding of why such networks are so resilient when part of the system fails. In a network where most of the nodes, around 80%, have few connections to others, and only a few nodes are highly connected, random failure of a node is most likely to affect a poorly connected one. So the system remains. What did I do? I'm sorry. The keyboard is right here, I think. So I want to go back, or do I want to show all your slides? Well, I'm sorry. Is this even more? How many? Was I just cycling through your slides as I spoke? Well, all right. All right. I'm going to stand back as I finish this then. I'm sorry, Leonardo. I hope I didn't give away the punchline. All right. All right, so Laszlo Barabazi, our Bachner lecturer, pointed out that natural systems, including cells and ecosystems, are often able to sustain basic functions under very high error rates as an inherent property of this topology. The desirability of creating human-made systems with a similarly high degree of robustness is obvious. In a very topical example, in the wake of Haiti, how can robustness be built into utility systems constructed in earthquake or hurricane-prone zones? Enter the civil and environmental engineers, including our speaker, who has done important research on this very issue, and so it is a particular pleasure to welcome him here today. Leonardo Dueñas-Osorio is an assistant professor in the Department of Civil and Environmental Engineering here at Rice. He's a native of Colombia and did his undergraduate studies there. He attained a master's degree in high-performance structures from MIT in 2001 and a PhD in civil and environmental engineering from Georgia Tech, or the Georgia Institute of Technology, more properly, in 2005. He has published a number of papers on interdependent lifeline systems subjected to natural or man-made hazards, including earthquake-induced power distribution system events and structural fragility, and regional hurricane risk assessment of single-family residential houses and utility systems in coastal cities. His work has also focused on the issues of cascading failures in complex structures and interdependent response in network systems. His research is partly funded by the National Science Foundation, the Department of Public Safety and Homeland Security of the City of Houston, the Shell Center for Sustainability, and Rice University. Recognitions for his work include the Science Applications International Corporation Award in 2005 for the paper entitled Interdependent Response of Network Systems, the Best PhD Thesis Award in Civil and Environmental Engineering from the Georgia Institute of Technology in 2006, and an NSF Early Career Development Award in 2008. As some of you may recall, he was an organizer, along with her board and Pedro Alvarez, of the engineering component of the DeLange Conference last year on transforming the metropolis. Today, he's speaking on complex networks, the key to resilient infrastructure systems. So please help me welcome Leonardo Dueñas-Osorio to the podium.
Well, thank you very much for the introduction, Susan, and also to the team at Scientia for the invitation. And thank you, the audience, for being present today. I am pleased with the opportunity to share some of the insights that we have gathered recently on how this emerging science of networks helps tackling some of the complex problems we see in infrastructure engineering. So what I will start with is, since the subject matter is infrastructures, I will define here, and by the way, the punchline was not given away yet, so rest assured. This definition is broad, but it's the less ambiguous that I have found, and it has two components: the facilities, services, and installations that provide or that are needed for functioning of the society. These facilities, services, and installations together form a system, such as the power system or the gas system, water system, transportation. And when I mean by functioning of society is governance, security, and economic vitality. So with this definition, then what sets apart infrastructures from other, let's say, entities in the built environment? Infrastructures, they are primarily large-scale, geographically distributed systems. That's the key feature of them. And because of that, then there are a number of unique characteristics, such as they are excessively exposed to natural hazards, to overuse or abuse of their components. They are also very complex to operate. Typically, the infrastructures are operated centralized manner. And they have been growing, but we are reaching a point where the centralized scheme is not working anymore. For water systems, we are reaching a point where the energy necessary to run mammoth water purification systems is just not going to continue that way. The other aspect is that because of this large geographical extent, you might see failures in multiple locations at once. And since the components are relatively repeatable, you have modules that they repeat themselves over and over. They tend to fail similarly, but in different locations, creating problems for adequate maintenance programs and also expensive to keep up the infrastructures. So with that in mind, let's take a look at the state of the infrastructures in the United States. The American Society of Civil Engineers, as its core charter, is to make a periodic assessment of the infrastructure. The last assessment was done in 2009, and you probably saw some of these values already, but this is a letter grade summary of key infrastructures in the United States, and the grades have been assigned by experts from the practitioner side, from the academic side, and from the membership of ASCE, which has more than 150,000 members. So we see that the grades are not that impressive. And if we do an average of all those, our GPA is D. So, if you have students with a D, you get alarmed, and that's how we are feeling. That for a while, we kind of forgot about the infrastructures and we let it get down, and now this is the situation. Granted, given the stimulus package and now the interest in aging infrastructures, some investment have been starting to emerge. But for many years, there was no investment. So what put us into this position? There are two main aspects that have led to the degrading state of the current America's infrastructure. The first aspect, grouped there in that blue rectangle, is that the demand for services has just been growing. In the last 30 years, we just keep demanding more and more from systems that are not keeping pace with that demand. In fact, they are declining in the amount of infrastructure needed to provide the increases in demand. For instance, for the power system, in the last 30 years, there was a 25% increase in energy demand. But the infrastructure necessary to keep up with that actually declined 30%. So we were in a diverging path, and that's not sustainable anymore. Again, recent years, I start seeing some important investments, but the gap that we created over decades is very wide. The second argument, that are the second two, or the last four lines there, last two of the 4 lines there, is an aspect that is not widely mentioned, but I think is very important, and is when we design infrastructure systems, we design them for a long life cycle. 50 years of service, 75, 100, some systems even more. Because of that long life cycle, relative to the time horizon of those who make decisions for maintenance and renewal, the time frames don't match. If you are a decision maker in a company or a politician, time horizons of more than 5 years are already too long. So if the systems are working fine, you just ignore them. And that's what was happening for several decades. We got compliant or complacent with the apparently reliable uses for all these systems. To illustrate this point, I just have this graph here. This is a typical bathtub curve that describes the reliability of engineering systems. When an engineering system is relatively new, I will use the power grid example again. 100 years ago, Edison and Tesla, they have a lot of trial and error period, and the failure rates here in the vertical axis, they refer the number of failures relative to the components that are working fine at any given time. Here in the horizontal axis, we have time. So at early stages, you see a lot of failures, then you learn about the system, and then you have a very long period of useful life where you don't see failures. This is the decades of neglect, I would say, but because we took it for granted. And then the components start wearing out, fatigue, excessive demand, and you start seeing a ramp up in the failure rates again, and that's the wear out period. And it seems we are entering into this. Some systems might be already here. Some of them might be entering into that range. So we have to do something. And the problem is complex because we have basically a large set of diverse infrastructure systems, all of them with large scale geographical coverage. And we need to come up with some ways to identify where to start. The problem is so complex that we need to start with that. Where do we initiate restoration of the systems? And that's where some of the ideas coming from the science of networks are helping us to make this informed focusing of efforts. If we keep with the traditional approach, it might be too complex to identify what is important. Network systems allows us to zoom out, look at the big picture of the problem, and actually identify ways that might be very useful to tackle the problem. So for this, after this motivation, the outline of the presentation it has 5 parts. The first 4 are the content of the presentation, and it will take probably 45 minutes or so. The first part is the topology of infrastructure systems. I want to make the point there that topology does affect function. In other words, when you look at a system as a single entity, you start identifying properties, and some of those properties affect the way the system performs. And we have ignored mostly that aspect from an engineering perspective. That's the idea to highlight. Then we start building a little bit on complexity. We see that systems don't work in isolation. They actually interact with each other, and that adds a layer of complexity that needs to be accounted for. Then another layer that you might start looking at is the dynamics of the system, how failures propagate. So one thing is to subject a system to a set of hazards and then see what is the residual performance of the system. And another one is to trace in time how the failures propagate. And then I will have this section 4, which is an exciting little section on emerging applications, some existing collaborations where we have taken these insights from network science, merged with engineering, and they are being applied to very practical problems. And then we'll wrap up with some concluding remarks. So with the topological aspects, this is the current transmission system of Harris County for the power transmission. We have the power plants are the lightning bolts, signs, electrical substations, and the transmission lines. The question is, the city has been growing, and this is the existing shape of the power system. Does that shape has any effect at all on how the system responds to external perturbations. So we embark onto some investigation of that. But before getting into the details of the topological investigation, I will remind you about ideal topologies of networks. And I think Susan already made reference to the scale-free networks presented here by the very Laszlo Barabasi, who developed the theory for the scale-free networks. And those networks are the ones that have a few nodes with a disproportionately large number of connections. That's one type of ideal network. There is another type of ideal network called the small world network, where nodes tend to have a very regular number of connections. So in other words, nodes tend to have the same number of connections on average. So what I will show you is those two ideal networks, the Barabasi-Albert or scale-free network in one side, the small world in another one. And those networks have the same number of nodes and links as the power system of Harris County. So that's the picture here. In the top right, the Barabasi-Albert, where you see the nodes with a disproportionately large number of connections. And in the left-hand side, we see the Watts-Strogas or small world network with very regular structure. So ideally, we have on the one hand the regular, and on the other hand, the one that has a dominating hub. The real Harris is here down, and this figure here is just a visualization. So it doesn't conform with the boundaries of the county, but it's just to show nodes not overlapping with each other. And we see visually that there are striking differences between them. And how can we start measuring or quantifying those differences? So the prime parameter that has been used to differentiate networks is the so-called vertex degree, which just goes and measures how many connections every node has, and you keep a log on the frequency of those. You create a histogram, and it shows some patterns. For instance, for the small world, the vertex degree distribution looks like a bell shape because there is a characteristic vertex degree. Most nodes tend to have a particular value here. In the scale-free, on the other hand, note that in the horizontal axis we have k being the vertex degree, and in the vertical axis the probability of seeing that vertex degree. But this is in a logarithmic scale, so you are spanning orders of magnitude here. And still you see some decent probability of observing nodes with a very large degree. In this one, you don't see high probabilities of large degree. In this one, you do. So those are the extremes. And obviously, the real networks are neither or neither of the extremes, but something in between. This is the real Harris. So we're going to start measuring some properties for these networks just to get a flavor on how the topology can be quantified, and then we are going to see if that topology really affects performance. Now, I have included here two metrics. That E is a metric called efficiency, and it's just a measure on how easy it is for nodes to connect with each other. So it's a metric that goes from 0 to 1, 0 being very difficult to connect, 1 being very easy. And in the small world network, you see that connecting, say, for instance, one node here in the top left and here with one in the bottom right, is pretty hard. You have to hop around a lot, and therefore the efficiency is relatively low, 0.02. Well, relatively speaking, the Barabasi-Albert has an efficiency of 0.19, because if you have distant nodes, you just go through the hub and pass to the other side. So that's a simple metric that allows you to quantify the visual or the topology. The other one is that gamma that I'm showing there is a so-called clustering coefficient. It measures how clustered is the network at the local scale. How much the neighbors of a node are connected with each other. And that's important because that helps with localized redundancy. So these two parameters, which both are scaled from 0 to 1, those are desirable properties in real networks. Let's see what are the values that we see for Harris County. So we have an efficiency of 0.14 relative to Barabasi, which was 0.19, so it doesn't look too bad. And the clustering coefficient, 0.04. You saw that Barabasi didn't have clustering coefficient. The Watts-Strogas have a very high one, but that's very idealized network. So it seems we have some clustering. Let's compare this with other network. of similar characteristics. So Harris County, in Texas, which other city can we look at? And Dallas, Fort Worth together is a good example, similar sizes. So here we have Dallas, Tarrant counties, and the properties are, for all intents and purposes, they are almost the same. Similar efficiency, similar clustering. Now we look for another city of a large scale, large population. So the next one would be San Antonio in Bexar County. And wow, we see here now an efficiency of 0.2, so it's getting pretty good. And the clustering is not that bad. It's relatively the same as the other ones. So why this one start offering more efficiency? And you actually see visually that this one has a topological pattern that is much different from the other ones. This one has almost like a ring and a mesh inside. So that's intriguing, and we wanted to see why that. But before I will show you 3 other cities, which are small cities. And the efficiency parameter is a little bit sensitive to the size of the city. So that's why I compare the first 3, because they are comparable to some extent. And the next 3 are going to be compared with each other because they are comparable among each other. But across is a little bit harder to draw a conclusion. So here is Travis County, the city of Austin, a little bit more efficient because it's smaller. But you also see that there is a backbone here, and it seems to start having that ring. So there might be topological features that contribute to that efficiency. Clustering is good. We have also El Paso, and we see that the efficiency goes up, mainly because it's a smaller network. But you see everything mostly concentrated here in this core. Clustering seems to be standard. And then Cameron County, this is for Brownsville, and you see very efficient one. And not only because this is small, but also because you start seeing that you have a hub here. It really resembles one of those scale-free networks, at least visually. So that provides a larger efficiency and a very low or a lower clustering. So power systems, they were designed for the same purpose, to provide power to the customers, but there was no, given the developmental pressures, they grew in different patterns, and these patterns show differences, and we can quantify them. What we want to know is, do these differences have impact on practical applications? So let me show you another parameter that is a little bit more intuitive in terms of performance. It's called a betweenness parameter. And I have a definition here that says quantifies the ability of the network to redistribute flow through the use of different paths. In plain English, it says the ability of the network to handle bottlenecks. So it's a little bit more related to the flow. And we see that Bexar County offers the best betweenness, the best possibilities to handle bottlenecks. So the intrigue grows, and then we decided, okay, given that we have Hurricane Ike here in Houston, and we had some hard data on the effect of Hurricane Ike on the power transmission system of Houston, we did the following experiment. We took San Antonio and put it here on top of Houston and subjected to a set of wind events and see how it performed. And these wind events, since they come to the Gulf Coast, then we also check Cameron County or Brownsville because it's there in the Gulf Coast. So we have 3 cities, all subjected to the same hurricane events, and we'll see how they perform. And this is the first set of results. In the vertical axis, we have this metric called the largest connected cluster. It's simply what is the size of the survived network. So if nothing happens, the survived network is going to be 100% of the original components. But here, as the wind speed increases, we see that the surviving or the remaining size of the network decreases. However, Bexar County did the best among all of them. Harris County did in between, and Cameron started losing it very early on. So when the wind speed is low, relatively low, I have it here in meters per second, and for your references, this dot here is Hurricane Ike, whose wind speed on average, maximum wind speeds were 110 miles per hour. So that will help you making the transformation. So for low wind speeds, what fails the most are the transmission lines, the links. And some networks can withstand that without seeing major losses on performance. When the wind speed really gets high, then we see declines for all of them, and that's because the electrical substations now start failing. And if they start going out of service, then the entire system really starts collapsing. But we see the advantages in Bexar County. Similar plot, now we are measuring that betweenness metric, but we see how much betweenness we are losing as the wind speed grows. So remember the betweenness, the ability to cope with congestion. So Bexar County does well also. And to confirm this ability of the Bexar County type of topology to handle not only the wind speed, but also to redistribute flow, we check the percentage of nodes that have abnormal flow. So when you have an intact network, you have a pattern of flow. When hazard strikes, then these patterns get disturbed, and you check how much, or if you exceed certain thresholds up and down of that, let's say, normal functionality level. And we see here in that, abnormally loaded nodes that Bexar County really does best in handling redistribution of flows. So bottom line here, topology does affect the functioning of systems, and not just with certain static metrics, but it does so for very relevant and practical problems such as hurricane hazards. What was the key for that? Well, we are learning from it, but the ring mesh topology is the key. When you have a ring, you have a very efficient way to communicate. When you have a mesh within the ring, you have shortcuts that allow you even more efficient. And that mesh within the ring also provides local clustering and provides the ability to redistribute flow via alternative paths. So it's not coincidence. It's really, there is a signature there that we didn't know, and it seems to favor the performance. So that's for this analysis on hurricanes. I will shift gears now to the following problem, which is interdependencies. So here we dealt with a single system, but systems don't work in isolation. They actually are becoming even more interdependent as we move on time, mainly because they are becoming more tied with the telecommunication systems. They are becoming smarter. You want to have more control, and interdependencies are just growing among them. So interdependencies are to stay. We need to then cope with that interdependence. These interdependencies arise mostly from geographical proximity. That's the obvious one. You connect with the systems as the ones that are next to you. But there is also the strength of coupling. There are some systems that are more susceptible to the interdependence than others. For instance, power is more influential on the water system than water system back to the power. Or the gas system, even though it interacts with the power, if there is no power, some of the gas compressors can use the same gas they are transporting to produce power, and they become basically independent. So there are some issues there with the strength of coupling. Operational conditions, we have diurnal cycles, seasonal cycles. There might be conditions of efficiency that require the use of one commodity more than the other. So as we move down this list, the subjectivity just grows. And then we have regulatory environment here. If you have pollution controls, that you might start using more water to control emissions and things like that. But that's a little bit less easy to quantify. So we're going to focus on the geographical proximity and a little bit on the strength of coupling. Let's go back to the example of Harris County. So we have Harris County, power transmission system there, but now we're adding all the water pumping stations of the city plus the gas compressors. And the problem really can grow in complexity. So since there is very little work on interdependencies, we started with a simpler problem. We have the full power transmission system, and we're going to be looking only at the power transmission system interactions with the nodes of the water system that use power. So we are not using all the pipelines of the water system, and we are not using all the pipes of the gas, just the nodes that consume power. So we're going to be focusing on how power affects water or gas. And in particular, I will be showing just power and water. So what is the easiest way to connect? The easiest way to connect water pumping station to the power system is to connect to the two closest electrical substations. By design, pumping stations need to have some redundancy, so they typically connect to two electrical substations. And because of economical considerations, you connect to the two closest ones. So I will show a figure here that just depicts that, how every water node connects to the closest ones. Just a visual representation. Here is in the top left. Is the so-called distance interface. So the interface here is the key because we are just looking at that subset of the whole problem. And you see that every water node, which is the blue, is connected to 2 power nodes. Some power nodes are connected to more water nodes. But the key is that you have a very dispersed topology for that interface. Now, that's the most likely to occur in practice. There is another one that it might be a little bit, it might be plausible, not as likely as the distance, but still plausible, which is connecting not only every water node to the closest electrical substations, but to the closest, and also at the same time trying to get to the ones that had the highest degree. So you are now trying to fulfill two requirements, closeness and high degree of the power system. So you take every water node, check 2 properties in the power system, and you connect to those. And the topology is very similar to the distance one. And again, these 2 then become the plausible ways to connect utility systems. There are 2 idealized topologies here. One in which we connect then every water node to the nodes of the power grid that have the highest clustering. So you are looking for closeness in terms of distance and also the highest clustering. And we see that the topology is still changing. And we can do the same with betweenness. You connect every water node to the closest and highest betweenness nodes. Why this? Because we wanted to see if there is an advantage to exploring different topologies so that we can enhance the interaction between systems. Interaction not only during normal operation, but also during distress. And here are the properties. I will focus on just a few of them. The rows that are highlighted a little bit on blue are the ideal topologies to connect utility systems, and the ones not highlighted are the most likely. So the first column looks at the LCC, that largest connected cluster. And we see that the idealized topologies really have a large connected cluster, which might be desirable because if you have a large connected cluster, you can, when you are dealing with interactions, the most connectivity you have is probably be to your advantage. Now let me jump not to substations, but to the third column here, edge length. We see that the idealized topologies for this interface use the largest amount of resources. Not surprising because you have to probably connect farther. That might be a downside, but now let's look at the last column here. This column is E, the efficiency metric that I was mentioning before. And we see that the idealized topologies to connect different utility systems offer a higher level of efficiency. So these idealized topologies have desirable properties not observed in the, let's say, ad hoc connections that we have nowadays, which are based on distance. So why not trying a solution where you start with the distance-based interface and try to add some nodes based on the betweenness approach? And that's what we do next here. So we take the distance, we take the idea of the betweenness, and we create a hybrid here. So this hybrid now ends up with 3 connections because you have the original 2 that are closest, plus 1 more that is closest and highest betweenness. Betweenness is being introduced here because then you can gain that additional efficiency that is desirable to operate infrastructure systems. It's very hard to coordinate systems that have very little communication between them. So we see the properties improve a little bit. LCC goes up, the efficiency goes up, the edge goes up, but bear in mind that here this edge is now for 3 connections per node. So what we do next is we then subject these interfaces to the same wind scenarios that we subjected the entire power system, just to see if there is an advantage to start getting ideas to control the interdependencies. Interdependencies are really neglected. Even the companies that own systems, they might own the power and the gas and the water. The different departments don't even communicate across each other. So it's an issue that needs attention. Let's look at the performance. This slide is a little bit, looks busy, but let me guide you through. So let's focus here on the bottom line. This bottom line is the performance of the clustering-based interface between power and water and subjected to the wind speeds. And here in the vertical axis, we are measuring a normalized efficiency. So it basically measures how much efficiency you are losing relative to your absolute efficiency. And we see that the clustering approach seems to be outperformed by everyone else. At the top, we have the distance-based connections. They outperform all other ones in terms of losing efficiency. And here in between, just focus on this dashed line. This is the hybrid that I just introduced, the dashed black line. So the hybrid takes advantage of the distance-based in the sense that it loses efficiency slowly. But we know that also in normal operation, it has high efficiency, and it facilitates communication across systems, which is paramount for interdependencies. So this is another example where we see this new information we get from the network's perspective might become useful and practical. Now, just to give some validation to all these models, I didn't mention, but these models in the background have a complete engineering engine which models the wind speeds and models the probability of failure of every component, every substation, every transmission line given the wind speed. It models debris from tree blowdown. So it models the roughness of the soil. It tries to capture the most important parameters from an engineering perspective. So to validate a little bit this one, look at this red dot here. This red dot is Hurricane Ike for the distance-based interface. Distance-based interface is the one that is closest to reality. And we see that the residual efficiency for that interface is on the order of 0.7. Well, here with some colleagues, with Bob Steiner that I see here and Devika Subramanian in the back, we did a large-scale survey after Hurricane Ike, not only asking about evacuation behavior, but a lot of questions on structural properties of the house, performance of the utility systems. And based on that data, we obtained that the loss of water was on the order of 35 to 37%, which it matches pretty good here. This is the remaining service. So, if we in the survey found that lose 35%, then the remaining would be 65, and we are very close to that. What is the message here? That networks, it seems they allow us to extract the most important feature of a complex problem. And those important features can be used to carry out these types of computations and focus you on the important problems at hand. They are a vehicle to guide the engineering community. That's how I see it. Then let's look at another problem here, the dynamics part. So the dynamics part is interesting because then you take an infrastructure system and you impose on it a shock, a quick shock, and then let's see how things go. So we're going to be looking at earthquakes, which can impose large initial shocks. Obviously, Texas doesn't have earthquakes, thank goodness. We have to go into the closest area in the United States that have earthquakes, which is the New Madrid seismic zone. And we're going to be using networks from Shelby County, where the largest metropolitan area there is the city of Memphis, which is mostly contained in this county. This is the power grid, just the representation of it, the water network. And what we do is we take these two networks, we connect them via geographical proximity and strength of coupling, and we subject them to different scenarios of earthquakes. Again, the modeling of the earthquakes and the damage of the components from earthquake, they are based on engineering and mechanics principles. And we monitor what is the loss of connectivity of the water system from failures of its own components and the added failures from the power system loss of functionality. So this is the kind of results we see. This is the connectivity loss in the vertical axis of the water system. And at time 0, nothing has happened. Time 1, earthquake occurs. And we have earthquakes of different intensities from 0.3 to 1. This scale of PGA is a standard metric for measuring the intensity of earthquakes. It's the peak ground acceleration. It's a percentage of the acceleration of gravity. So we have the event. This is failure of the components due to the direct exposure to the earthquake. Then the next cycle, cycle 2, is the first round of interactions. So the power starts affecting the water because some power components failed and they stopped providing the necessary pumping power for the pumping stations. And then the water system might affect back the power, and the power back the water, and you have a cycle here, and this one stopped relatively rapidly. After 4 cycles, things are stabilized. This is for a low coupling between the power and water. If we go to high coupling, this is the vertical axis, again, connectivity loss. With high coupling between the power and water, we see that the trigger occurs, but then the first cycle of cascade really induces a lot of extra connectivity loss. And then we have a few cycles where things keep going back and forth until they stabilize. So what is the message from this part of the cascading failures here? That the largest amount of additional damage from interaction occurs really at the very first few cycles. What would be the best strategy to control that? To stop the cascade to even initiate. So what we might need to be doing is, obviously, interdependencies is not going to be avoided. They are actually increasing the interdependencies. But what we can have is ways to decouple the systems when they are subjected to these external events. You can island the systems, you can decouple them, or you can actually identify which components participate the most in these interactions and strengthen those. So I will show you what happens if you actually strengthen some of the components that fail more often. So here in this slide, let me show you here to your right, we have the water system, and we strengthen all these components that are to the north of the county, because the new Madrid seismic zone is somewhere to the north of that. So these nodes contained here are the most exposed. You go and strengthen them, and you also decouple them from the power system. You can provide alternative sources of power. We monitor then the connectivity loss. Here I have then 2 plots. Top is for before any retrofit action, and the one in the bottom for after. And the plot is showing the probability of seeing a level of connectivity loss given a level of seismic intensity. So just to make it easy for you, let's suppose we have an earthquake with a 0.5 G PGA. So we are here. If we do nothing, the probability of seeing, let's say, 90% of connectivity loss, so we come to this plot here. This line is the 0.5 PGA, and we see that the probability of seeing 90% connectivity loss is almost 1. So for sure, you will have 90% connectivity loss. If you do this small scale improvement, then we see that the probability of 90% connectivity loss is only 10%. So what we have been seeing throughout this analysis, that networks are also amenable to small modifications at the local scale, and suddenly you see that their effects propagate big time at the global scale. They are obviously very efficient at propagating effects, and this should be taken advantage of. However, the same way we can propagate positive effects, negative effects can do the same. So we might have very small perturbations and then see large-scale consequences, such as in blackouts. The one in 2003 started because of a tree that made a short circuit in one of the heavily loaded lines. That's very benign triggering event, but 50 million people then without power. So we should take advantage of that ability of the networks to amplify effects from local to global, hopefully in the beneficial side of things. Let me show you then another example of this sort of dynamics. We have another network here, one more and we see this network is a typical system used by electrical engineers, and it has been extracted with real features. I didn't put here the E and the gamma, but if you are curious, the E for this network is 0.2 and the gamma on the order of 0.12. So this is a pretty good system relative to the other ones we have seen. And if you look at it, then you see that there are some nodes that have large connectivity, and you don't see too many nodes that are just hanging alone. You sort of see some envelope there. That might help. Anyway, that aside, then what we are going to do is we take this system, and we're going to subject it to 2 kinds of hazards, earthquakes and lightning. The reason for this is we want to see, obviously, different hazards, but we're going to monitor this system over a period of 50 years. And we are putting this system in the northwest United States, in Washington state. Now, in 50 years, you are not going to see large earthquakes. Large earthquakes, you see them in a time frame of thousands of years. So in 50 years, you might get some tremors, but nothing serious. But those might be enough to just have small triggering event. And that's what we want. We want small triggering events to see how bad they propagate. And we also have lining in that area. Let me show you the lining map for the US here. And for that Washington area, we have the lowest lining flash density of the entire country. But still over 50 years, you might see important lining. So we do that simulation over 50 years. Every little event that occurs might trip some transmission lines or might damage some substations. And what we monitor here is the ability of the network to redistribute the flow. If you take one line, that power that was going through that line has to redistribute somehow. And if the network can take it, fine. If not, it will trip other lines and I think cascade large scale. So similar to the cascade in interdependent systems, this is for a single system. 0, nothing has happened. 1, the triggering event occurs. 2 and above is the cascade effect. But here you see that the largest loss or connectivity loss occurs for lining. So lining is a very benign triggering event, but if it hits in the Achilles heel, you can get very large consequences on the system. One thing here, so if the systems are susceptible to these cascades because of not being able to handle capacity, the standard engineering solution is let's make it bigger, let's increase capacity. And sure enough, we can increase capacity. So the next slide shows how the systems perform as you increase capacity. And what we are monitoring is the steady state connectivity loss. So you take the systems, subject them to the 50 years of simulations of earthquake and lightning, and you monitor the steady state. And for every system, you check different levels of capacity in their lines. So here we go with that plot. In the horizontal axis, we have the tolerance parameter alpha, which if alpha is 0, that means you are working at full capacity. If alpha is 1, means you are working at half capacity and so on. And the lines are measuring that mean connectivity loss after the steady state. And we see that if we increase capacity to double it, you can actually decrease a lot the mean connectivity loss. But then after that, it really becomes not important, the investment. So what else can we do to really bring that connectivity loss down? So we can go back and look at the topology. And here, because of operational systems, Windows and Mac, one of the figures doesn't show up properly. But here what we are looking is the same plot. Look, this same plot, this is for, I will retain the blue line, which is for earthquake of that IEEE system. So you will see that line exactly here. And I am adding then systems that are a little bit different. They share the same number of nodes and links of the IEEE system, but they have an inherent topology that is idealized. And one of them is a tree that you don't see here, but a tree is just a minimally connected network. You only have enough links to connect all nodes, but you don't have loops, you don't have any kind of redundancy. So the performance of that tree, on average, is pretty flat. But then you also have a perfect grid and a grid with some extra connections. And you see that if you combine tolerance parameter of 1, you double capacity, and you have some measuredness. These grids add this local measuredness. If you add some of that, you can bring the mean connectivity loss much down than just by doing capacity. So again, the lesson here is we can exploit these topological features combined with our traditional approaches and really improve otherwise difficult objectives of performance. Now, with this, let me move on to some exciting new applications that we have been working with colleagues, mostly here at RISE, and I've been very grateful with that. The first one is, after doing all this work, most of the work is doing through numerical simulations and engineering models, but once you gain insight about the problem, you might step back and say, well, maybe we can tackle some simpler problems, but we can tackle them in closed form. Why closed form? When you have closed forms, you have much more power to explore things. You can explore all ranges of inputs. You can explore sensitivities. It widens the possibilities that you have. Numerical simulations are fantastic, and we do a lot, but they are expensive in terms of computational time. And if you have closed forms, you remove that barrier of time, and you really can get crazy about it. And Here what we are looking at is a power transmission system again of Harris County. And in the background, you see all that blue now. All those pixels are the distribution load points. Those are the, let's say, the users of the power. So what you have is the green dots are the electrical substations, for instance. And from electrical substations emanate radial feeders. And those radial feeders then have some laterals that go to the load points. So here to your left is a cartoon of that. The green dot is the electrical substation, and the electrical substation has some main feeder, which is this vertical path, and that main feeder vertical path then has some laterals that go to the actual customers. Now, in reality, you don't have systems with just a single main feeder. You might have systems where the substation, which is this thick line, has 3 or 6 or even 10 feeders. It depends. But what we have been able to do is these feeders typically have a radial configuration. Radial in the sense that you start at the substation and then everything flows downstream to the load points. That feature that you see when you look at it from a network viewpoint can be exploited, and this has been worked with Javier Rojo from Statistics. And we have been able to have this closed form solution that has been elusive so far, but now is available, and it can provide you the exact number of customers that you might have with service, given some information about the failure rates of the different components. Before, what you were able to do was to get some average value of the number of customers that you might expect without power. But now with this new equation, you have the entire realm of possibilities. You have a probability distribution of it. And that's very powerful. Just to show you some results of that, this is a PMF, or a relative frequency chart for the number of customers. That little system has 3,000 customers, and this solid pink line means that the vertical path is very reliable. It has a reliability of 1. So if you have a reliable path, the only failures occur at the laterals, and therefore you are very likely to see most of the customers with service. You see that everything is shifted towards the right, meaning that it's very likely to see a lot of customers with service. If you have a vertical path that is not that reliable, 0.5 or so, then the whole PMF or frequency plot shifts to the left, meaning that the majority of customers with service is small. Again, before you only had a mean value, now these insights from networks have allowed to show this bigger picture. One following application, this is bridges. So this is being worked with Jamie Paget that I see in the audience. And I'm sure you have a bold imagination and you see a network there, correct? Bridges actually work as networks. Here we have the columns. We have these endpoints that are called the abutments. These supporting points, the triangles, are fixed supports called fixed bearings. And then the circles here might be elastomeric bearings that actually move to allow for displacement and temperature and accommodate a lot of other things. So we have the system. In a logical sense, a bridge made out of all these components, it works only if all components work. If you have one component that fails, the whole system fails. So the network abstraction of this bridge is a very simple network. It's just a chain. Easy enough network, but nonetheless a network. So in the network sense, if you have a connection from this initial point to an end point, you are fine. If any component in between has failed, you lose connection, and therefore you are not fine. Adapting that equation that was developed for the radial systems of the power grid to this bridge, now we are able to check all possible ways in which individual components fail, or pairs of components fail, or triple, or 4 groups of 4 or 5. All possibilities. They can be checked very efficiently. And then you can learn about which components really contribute to the system performance. So what we did with Dr. Paget here was subject this bridge, which is a typical bridge for the central and eastern part of the United States. It's a multi-span continuous steel girder bridge, which is going to be subjected to earthquakes typical of the central United States, that Mid-America region. And For that suite of earthquakes, we're going to check what components are most sensitive after exploring all possible combinations of them. And this is the sort of plots we are getting, which we seem are very informative. Let me walk through that. This is a sensitivity index. It measures how sensitive a component is to the overall performance. So 1, the component is very important, 0 is not. And we have the different components here. The acronyms are not that great, but col is column, FL and FT are the fixed bearings in the longitudinal direction, fixed bearings in the transverse direction. Then the E's are elastomeric bearings in the longitudinal, elastomeric in the transverse, and the A's are the abutments, those ends, and you have different ways that the abutment performs in passive action, active action, transverse. But what we can see here, and was enabled by this network approach to seemingly unconnected systems such as a bridge, is that for the different levels of PGA, remember the levels of hazard, you can really track what is the contribution of every component. And we see these changes. We see that at low levels of PGA, the abutments are more important. But then if you increase the PGA, in this case for moderate damage of the bridges, you see that the columns start getting important, or the bearings. This is the kind of practical information that is used by DOT representatives or people in the highway administration. Another application, here with colleagues Bob Stein, Devika, and another colleague from Baylor College, his name is Jerry Fowler, is evacuation behavior. So this plot that you see here is the actual evacuation map for Houston, or for the Houston-Galveston area. And what we want to highlight is that all this area, most of Harris County, basically has a white color there saying don't evacuate. But that's not enough to prevent people to evacuate. What we have seen is that all the people that is living in this area, they end up evacuating. We saw it in Rita. It happened in Ike, but it was not prominent because Ike was so small, relative to a category 5 or so. So that didn't trigger a visible amount of non-compliant evacuation people, but they did evacuate. And we have some proof from the surveys that we conducted. But let me show you what is the network component of this. So we are developing an online tool where we are going to fill the gap. Now the whole county is going to be shown different risks. And we use the network model for showing the risk of power outages through the county for a given storm. Here is a category 5. You plug in your address and you get your risk score. You can get the risk score for a storm surge, for rainfall flood, for wind. And this is not all. What we are really after is, we are going to start some beta testing soon. What we are after is monitoring the keystrokes and all the usage patterns of the people that come to the site. Why? What we want to check is the patterns of people's addresses, because that will provide a lot of information on the family, friends, and neighbors they care for. And this will give us a picture of the friendship network, if you will. Why are we interested in the friendship network? Because, again, from the survey data that we have, friends and neighbors influence the most evacuation behavior in people that do not need to evacuate. And if we have a better picture on how that clique of people plays around the citizens, then we might be more efficacious about informing them and preventing that undesirable so-called shadow evacuation. People that evacuate that don't need to. So I think with that's the last application that I had here. Let me go through some conclusions to highlight the points. First point, topology does affect functions. So that's the lesson. I'll be happy if you take it with you. Then also we see that networks are very ideal entities for amplifying local phenomena at a larger scale. We saw that we can amplify benefits, but unfortunately the same medium can be used for amplifying detrimental effects. Now, network abstractions really provides us a mechanism to tackle otherwise very complex problems, such as the interdependencies, the dynamics. It helps engineers to set a starting point that is very reasonable and that will lead to hopefully productive solutions. And the last one, which is this way where when you have a tool and then it seems that everything looks like network, even bridges. We're still looking for applications, but it does, some problems really can be cast in that network light, And we see that tools that were not available before become available all of a sudden and can help with standard practices of maintenance and rehabilitation and retrofits. Acknowledgments, obviously all this work has been really with a very rich set of collaborations with faculty. I mentioned Javier, Devika, Bob, Jamie. My students, I see them all around here, Isaac, Sin, Kevan, postdoc, Mino Yang, and a bunch of undergraduates that have been in and out, but I'm listing here the ones who have worked with us recently. So with that, I really appreciate your attention, and if you have questions or if you want some of the technical papers that back up all this work, just send me an email. Thanks.
All right, that was wonderful. I'm imagining there will be questions. Will you take your...
Absolutely.
You identify? Okay, just a few minutes of questions.
Yes. Yes, please.
So how much are the managers of these infrastructure networks worrying about these things? And for example, the difference between the power networks, the reliability of the power networks between San Antonio and here, is that because they designed it better or just because they happen to connect it that way for other reasons?
Yeah, for this part, it just happened to be that way. It's been this organic growth, and now we're asking the question if this growth has led to differences. Now, something has been brought to my attention. San Antonio has a little bit more planning and zoning than Houston does. So that might have affected to some extent. Now, with regards to the actual public utility people, in the past it was very hard to really even, when they have a problem, they just want to deal with the problem at hand. We have been talking with people from the Memphis area, Memphis Light and Water, here in Houston with Centerpoint Energy. They have been very gracious, but whenever something urgent comes, they really divert their attention to that. So we have been after other ways, and fortunately, through the American Society of Civil Engineers, it has a technical council on utility systems. And obviously, from that viewpoint, the problem has really gained a lot of clout and attention. And there is a new committee that is going to be dedicated to studying the interdependencies between systems. Now, the Technical Council already has membership for every one of the independent systems. It has membership for the power, for the water, and this interdependent has the chart to start bridging the gap. And I'm fortunate that I will be heading that endeavor starting this year. So we will see more. This membership in ASE combines both practitioners and academics. So we will see a little bit more of receptiveness from them. Yes, please.
Could you give us an idea of what the mathematics is behind these calculations? Is it a Monte Carlo calculation, or can you make some kind of a mathematical statement about the advantages of one model over another?
Right. So for the numerical simulations, they are mostly Monte Carlo based. Since the amount of Monte Carlo simulation is large, we try to then explore efficient ways to do it. So we try importance sampling, more recently the subset simulation. So we try all sorts of ways to make numerical simulations affordable. For the closed form, they really are based on combinatorial arguments. So you have a bunch of sums of products, but you can add things that provide more realism, such as correlations between the responsive components. So you can take that sums of products and you can add some integration to capture correlations. So the basic tools, I would say, for the closed form is combinatorial approaches. That's where we are. For the numerical simulations is Monte Carlo based, and we strive to make it more efficient the way we can. We even used parallelizing. We are trying to use the supercomputers, but that's sort of the basis. Yes?
Well, Leader, along that same line, are you able to actually calculate the uncertainties of these estimates so that you can look at how the different predictions are separated,
yes.
As well as what about, these are pretty complex simulations, what about model validation?
Right, so for the first part, Monte Carlo simulation really has that advantage that provides us some of the allows us to quantify uncertainty. For the closed form solutions, it was not possible until these recent endeavors where we get the full uncertainty. That was the drawback of the existing analytical solutions. So I think we are heading towards that path. Now, these expressions that we have for the analytical solution only apply to radial systems. And those are probably the most basic radial systems. But nonetheless, they are the starting point, and actually we can do those calculations very efficiently, and we hope to start adding loops. That's the next step in complexity. So uncertainty for us as engineers is our contribution. If we don't bring the uncertainty to the table, then we are not basically adding anything else. For the second part, now I forgot.
Model validation.
Oh, the validation we have tried. For instance, I showed for the power grid the first part of the simulations that where we took Harris County and subjected to the hurricanes. We had the data for Ike, and we actually simulated all our model with an Ike wind field, and we compared the two things. That's in one of the papers. The error was relatively small, was on the order of 15% or less. To some, that might be a large error, but for the complexity of the problem, we were very happy with that. So the errors were on the order of 20%. For the interdependencies, I show this, it's one data point, again, with Ike and our survey, and they match. So at least it gives us hope that the network models are able to capture the essence. And I think that's been the success of the network approach. That Barabasi model is not a complicated model. It's simple enough to capture the essence, which is the hub node, and that it grows with time. Things like that. So I think it seems we are capturing the key components, and as we understand them and evolve them, we can start adding a little bit more of the other complexities. Yes, please.
November 9th, 1965, I was in college in western Pennsylvania, 5:30. The lights went out and came right back on again. And then went home and found out that everything else in the Northeast was blacked out except Pennsylvania. The explanation was that the links were weak. Pennsylvania was not a good networker. It wasn't a good participant. So it stayed on. Now, much more recently, I think a few years ago, there was a power failure in Ohio. Pennsylvania is much better connected, so they got to participate in the blackout. So it seems to me as you go to a larger and larger system, they don't want to spend the money to take care of the extremely rare events. So all you're going to do is make the catastrophes a whole lot bigger. When our whole nation is totally interconnected, then your whole country's going to go black. So the question is there any way to fix the problem that when you build what do they say, the bigger it is, the harder it falls?
Right, no, that's very true. The more connected you are, basically the more efficient your medium is to transmit both positive and negative things. So what I think we as engineers, not just myself, but we are trying to be mindful is of these approaches that allows us to partition the systems. I mentioned it for the interdependencies. That's a very efficacious strategy where the moment you start noticing abnormal operation, you just should go in protective mode and unplug yourself from everything else. That is being used to some extent in the power systems, where you can sacrifice some components, but isolate others that you might be able to balance power supply with demand. However, the technology, even though there are some supervisory control and acquisition data devices that provide you information on real time, pseudo real time of the state of the system, they are not that great to really do this islanding and manipulation. This really takes minutes or tens of minutes, and you cannot avert a blackout such as the one in Ohio with that time frame. A lot of human error went into that final consequence. So we expect that as this concept of the smart grid comes in, we are going to be much more aware of any signs of abnormal operation. And hopefully we can pick up of any disturbance and start taking corrective actions. Because otherwise, I agree with you, otherwise the systems, the more connected they are, just the easiest to propagate anything is. Yes?
Of course, if you do that wrong, you get a disaster like the AT&T network. Right?
That's very true.
It took itself completely out.
Yes. No, that's true. And another concern is the cyber security. The more you rely on IT, you see all the hacking activities is so prominent. We don't know what we can get into if someone starts hacking some of these systems. You might well have shut the entire interconnection of power in the United States. Now, this is not for just power. Most utility systems are getting into that. The water, the gas, even transportation. We are monitoring much more prominently now some key bridges and trying to anticipate things. But cybersecurity is an aspect that needs to be hand in hand with the engineering reliability. And to be honest, I haven't seen much of that, except for some folks here at Baker that have raised that concern. But not in general, engineering discussions, I don't see the IT cybersecurity part being raised as a major concern.
Leonardo, thank you so very much.
No, thank you.
All right. I want to thank Leonardo for putting together such a comprehensive and interesting presentation that has certainly opened my eyes to many things, among them other models than Barabagi's, which is probably good for me. So, and also the alarming report card for our nation, and that proneness to failure curve on the right-hand side of that really gives us cause for considerable pause. But thank you for your good work in protecting us from the effects of the increasing rate of failure, which is quite important. So thank you all for coming, and I hope that you will also, am I cycling through your slides again? You liked them the first time, why not once more? So thank you all for coming, and please, we hope to see you next month when Carrie Ward will be speaking about networks of empire. Thanks very much. And join us at the reception.
This program is protected by a copyright and may not be redistributed in whole or in part without the express written consent of Rice Digital Media Services.